Welcome back to Advanced Functional Programming. I am Daniel, and in this video we're going to be talking about currying and partially applied functions, or partial function applications, depending on which name you prefer. Without any further introduction, let's dive into our favorite development environment, and let's explore what this actually entails. Alright, so we're in IntelliJ again, and we're in the Advanced Functional Programming section, and thus in the Part 2 AFP package, where I will ask you to right-click and create a new Scala application. So right-click New, create Scala class, and we're going to call this Curries and PAF from partially applied functions. Let's make this an object, and let's make this guy extend app. Okay. Cool. So let's talk a little bit about curried functions. You already know, or should know by now, about curried functions. In the previous course, we introduced the concept of functions returning other function as results. So if I say, for example, a super adder, I'm sure you remember this this example, which is of type int arrow int arrow int. That is to say, this is a function taking an int and returning another function which takes an int and returns an int. And if the implementation here is x arrow x plus y, then this is a curried function. And you can define auxiliary functions such as, for example, add3 based on super adder, and we can call the super adder function with fewer parameters. So we can say val add3 is super adder3. That is to say, this is a function from int to int, which is y arrow 3 plus y. Okay, and then we can simply print line add3 applied with some number, say 5, and this will return the number 8. So if I right click and run this, of course I'm going to see the number 8 to the console. Okay, and we can also call super adder by itself with multiple parameter lists, such as super adder with 3 and 5, and this will just create the same result. All right, so we see 2 8s here in the console. So the super adder here, like I said, is called a curried function, in the sense that it receives multiple parameter lists, and Scala allows the definition of curried methods out of the box with multiple parameter lists. For example, if I define a curried adder with a def, not with a val, and this takes a parameter x, which is an int, and a parameter y, which is an int, notice that they're in two different parameter lists. And if this guy returns an int, and the implementation is x plus y, then this is a curried method. Okay, and if we want to use this method with fewer parameter lists, we can just say val add4, which is of type int arrow int, is curried adder with the number 4. And this will return the function remaining after the first parameter list, which is y colon int arrow 4 plus y. But here's where it gets interesting. This thing doesn't work if I remove the type annotation here. So if I cut this out, and if I right click and try to run this, the compiler will complain because it says missing argument list for method curried adder in object curried PAF. Unapplied methods are only converted to functions when a function type is expected. You can make the conversion explicit by writing curried adder underscore. We'll get to that in a second. So what the compiler is complaining is that we're attempting to call this method with fewer parameter lists than the compiler expects. So curried adder has 2 parameter lists, but I'm only supplying 1. And at this point, the compiler is confused. What am I trying to define here? Am I getting the result of curried adder, or am I defining a function? So if I bring the type annotation back, the compiler is happy because I've defined this as a type annotation, so the compiler figures out that what I actually want is the remainder function after curried adder with fewer parameter lists. But what this actually does behind the scenes is called lifting. So the original problem is because the curried adder is a method, it's a def. This is a method, people. It's a def. When you call a method, you need to pass in all parameter lists. But what we wrote here is that we converted a method into a function value of type int arrow int. Now, the point here is that we want to use function values in higher order functions. This is the whole purpose of functional programming. We can't use methods in higher order functions unless they're transformed into function values. Now, that's a limitation of the JVM because methods, like we wrote here, are part of instances of classes, or in this case, the part of the singleton object curries PAF. So methods are not instances of function X themselves, all right? So transforming a method to function is called lifting, which is what we've done here, which is also known as the more technical term called eta expansion. So eta expansion is a simple technique for wrapping functions into this extra layer while preserving identical functionality. And this is performed by the compiler to create functions out of methods. Right? So functions not equal methods due to the JVM limitation that I spoke about just a minute ago. So eta expansion is what the compiler does when you say, for example, def inc with a number and returns a number plus 1. All right. And when you use this inc method as a function, as in list123.mapInc, all right, I'm sure you've used this a lot of times, but what this actually does behind the scenes is that the compiler does eta expansion for us, and then it turns the inc method into a function, and then it uses that function value on map. So the compiler basically rewrites this as x arrow inc x. All right, so when you say map inc, actually the compiler converts that method into this kind of lambda. But we don't really care about that in 99% of the time when we use methods in higher order functions. But you are no ordinary people, you are rock stars, and now you are aware that this happens, all right? Now, why did I tell you about eta expansion? Because, let's get back to curried functions. The way that we can force the compiler to do eta expansion when we want is when we want to use partial function applications. What do I mean by that? If I want to use this curried adder method, and I want to define a function value called add5, which is curried adder 5, I can put in an underscore. So notice this underscore here, and this will tell the compiler, hey compiler, do an eta expansion for me and turn curried adder into a function value after you've applied the first parameter list. So this will tell the compiler, hey, do an eta expansion for me and convert this expression into an int arrow int function. And if you hover over add5, you'll see that add5 is automatically inferred as int arrow int. And also, if we actually recompile this code, the compiler will be happy this time. Cool, so let's take a small break and do some exercises. Let's say I have 3 different ways of adding 2 numbers. Via a function value, let's call this simple add function, which is x int y int arrow x plus y. So a simple lambda. Then a def with simple add method this time, and this receives 2 parameters x int y int, and the implementation is x plus y, and a curried add method, which receives 2 parameter lists x int and y int in 2 separate lists, and the implementation is the same x plus y. All right. Now, having these cute add versions here, what I want you to do is define an add7 function value, which is of type, of course, int arrow int, whose implementation is y arrow 7 plus y. Okay, and I want you to implement add 7 out of these 3 queued addition versions. And I want you to implement as many different implementations of add 7 using the above as you possibly can. Be creative. All right, so pause the video and let's see how many different add 7 versions you can come up with. All right, and I'll get back with some solutions. All right, so let's see what we've created. All right, let's create an add 7, which is an x int arrow, simple add function of 7 and x. All right, this is the simplest solution. And you can use, instead of simple add function, any other of the 3 options that I've given you at the beginning. All right, so you can have 3 add 7 versions right off the bat. All right, another way of writing add 7 is to say, I'm going to name this add 7 underscore 2, is simple add function dot curried, and this turns this function into its curried version with multiple parameter lists. And if I call it with 1 parameter, then that will turn it into the remainder y arrow 7 plus y. All right, so you know about the curried method on function 2. Another version of add 7 would be to say add 7 underscore 3 would be to say curried add method with the first parameter 7 and then put an underscore. So this is the partially applied function, which forces the compiler to do eta expansion for us, which will lift the method into a function value. Okay, an alternative syntax here is to say curried add method with 7 and with underscore here in parentheses. This will trigger the compiler to do the same thing. So this is, again, a partially applied function. All right, so this is alternative syntax. But this alternative syntax with underscore also works for non-curried methods. And here is where I will cheat and give you some versions here that you probably had no idea existed. So I'm going to say add 7 underscore 5 equals simple add method, and I'm going to pass in the first parameter, and the second parameter I'm going to use as underscore of type int. So this is, again, alternative syntax for turning methods into function values. So this underscore colon int still forces the compiler to do eta expansion for us. So basically it turns simple add method of 7 and underscore into a function value saying whatever the underscore is, put it in the function parameter for the function value that I'm constructing, and return whatever simple add method returns after the application of 7 and that parameter. So this makes the compiler rewrite it as y arrow simple add method with 7 and y. But I'm not finished, because this cute little syntax is applicable for functions themselves. So if I say val add 7 underscore 6, I can say simple add function with 7 and underscore colon int. So this works as well. All right, so this underscore colon thing forces the compiler to turn either a method or a function into another function value. All right, so the underscore forces the compiler to do eta expansion. And besides these 6 versions here, there's a whole bunch of potential implementations that you can create out of combining the function with the methods, or even all of the options that I've given you at the beginning of the exercise. So if you're feeling creative, take some time, and after that, let's get back to partially applied functions, because there's more I wanted to show you. All right, so as you saw in the exercise where I cheated, and I'm not even sorry, you saw that functions and methods can be partially applied with underscores, and this returns functions with a smaller number of parameters. Underscores are actually quite powerful. If I say, if I define a function or a method, if I define a method that concatenates some strings, let's call this concatenator. And I have a string, and then another string, and then another string. And this just concatenates the three, so A plus B plus C. Then I can create function values by supplying underscores anywhere in the function application. Watch what I'm writing. So if I define a function value called, let's call this insert name, equals concatenator with hello, and I'm leaving an underscore, and then I'm supplying a parameter, comma, how are you? Then this is a function value where I can supply a single parameter, and the result will be the result of concatenator after supplying the parameter inside this underscore right over here. So watch it in practice. If I print line insert name with Daniel, then this will say, hello, I'm Daniel, how are you? All right, so if I run this, it will say, hello, I'm Daniel without a space. That's such a pity. How are you? All right, so you saw Daniel being injected here into the underscore. The underscore tells the compiler, hey, compiler, do an eta expansion for me, and this will turn this expression into a function value saying x string concatenator of first, hello, I'm x, and how are you? Excuse the pseudocode. All right, so you got the picture. The underscore forces the compiler to expand this method into a function value where the parameter here is injected into the underscore. I can actually create function values with multiple underscores. So if I say val fill in the blanks as being concatenator with hello and then underscore string and underscore string, then each underscore will be a different parameter in an eta expanded xy arrow concatenator of hello and x and y. All right, so each underscore will be a different parameter. And if I print fill in the blanks with Daniel and Scala is awesome, and let's just put in some spaces here. Then if I run this, you'll see that each parameter is injected into each of these underscores. So hello Daniel, Scala is awesome, which it is. It is true. So eta expanded function values are very good for very granular APIs where you want to support the most general function, like concatenator here, but also smaller, more concrete functions, like concatenator with some blanks already filled in. All right. Now, before we wrap up this video, let's do some exercises. And I want, as the first exercise, to process a list of numbers and return their string representations with different formats. And I want you to use the %4.2f, %8.6f, and %14.12f with a create formatter function. If you don't know how to format, you can say %4.2f format math.py, and that will format your string. So if you print line this guy, you'll see the number 3.14. And if you do a more precise format, like 8.6, you'll see more decimals here in the console. So what I want you to write is a curried formatter function. See? I want you to write a curried formatter function that takes a format and a number, and then I want you to apply that curried formatter on a list of numbers as a higher order function. Think about how you would do that. All right? So that's exercise number 1. The second exercise is more exploratory, and this wants to dive into the difference between, and there are two differences that I want to explore here: functions versus methods, and parameters, which are by name versus 0 lambda, which is a common source of confusion in Scala programmers that I've seen. So here's what I want you to do here. I want you to define two small methods and then 2 other small methods. So I want you to define a method called by name, which receives a parameter by name. Right? And this should return like n+1. We don't really care about the implementation. We only care that this by name method receives a by name parameter. Okay. Then a by function returns again some int, but it receives a function as a parameter, a 0 lambda. So nothing to int. And this is like f+1. I don't really care. Okay, so these are the methods that we will use, and then we'll provide the applications of 2 other methods. Method called, let's say, method, for lack of a better name, which returns an int, and let's say this is like 42. I don't really care. And a parentheses method, which receives parentheses, although it doesn't receive parameters, and this is also an int, and the implementation is something like 42. So the exercise wants you to explore calling by name and by function with the following expressions: an int, a method, like this method, the paren method, a lambda, and a partially applied function. And I want you to figure out which cases compile and which don't, and why. All right, so pause the video and work through these 2 exercises, and I'll come back with solutions. All right, so let's take them in turn. The exercises are pretty simple themselves. So for the first curried formatter here, all we need to do is define a curried formatter, which takes a string as a formatter and a number, which is a double. And this will return a string, and the implementation is going to be simply s.format number, as I showed you in the example, right? And the numbers here that I'm going to use are going to be some high precision numbers, like math.py, math.e, 1, a really high precision number, 9.8 or something, and a really low decimal number like 1.3 e minus 12, which is really no. All right, and let's define some formatters here by using these formatters: the partial application that we've learned in this video and the curried formatter that we've defined here. So if I say val simple format, that's curried formatter with %4.2 f, and then I put in an underscore, then that tells the compiler to lift this this method into a function value. And again, I can define some other formatters here as well. So if I define some serious format with curried formatter, and as an argument I'm putting in percent, what did I say, 8.6 f underscore. The underscore is very important. And precise format, which is curried formatter of percent 14.12f underscore. So you see how this partial function applications allow us to reuse curried functions in a variety of ways. All right. Then if I print line numbers map, for example, simple format, then I'm going to see all these numbers in the 4.2f format. So if I right-click and run this, I should see 3.14, 2.72, 1.00, 9.80, and the last number is too small to fit into the precision. But if I use the precise format, then that should fit in. So we have 3 point a lot of decimals, 2 point a lot of decimals, 1 point lots of zeros, 9.8 lots of zeros, and this guy with lots of zeros and then a 1. So the 1 barely fits in. The purpose of this exercise is to show you how curried functions, curried methods actually, can easily be reused with partially applied functions with underscores. Now, if I use this precise format here, I can also use it like this, but I wanted to show you something. Now, the compiler says anonymous function convertible to a method value. This is a pretty cryptic message, but what the compiler basically says is that this underscore is useless. So I can actually remove it, and the compiler will do the eta expansion automatically because I've passed a method with fewer parameters as an argument to a higher order function. So compiler does sweet eta expansion for us. But you've learned about eta expansion, all right? Cool, so this was basically the first exercise. Nothing too spectacular about this. At the second exercise, things are, again, not rocket science, but there are some differences that I want you to be really clear about. All right, so let's get down to it. So if I call by name with a number, say 23, this is perfectly fine because 23 is a by name evaluated expression. So this is okay. If I call by name with method, this is also okay because the method will be evaluated to its call, that is 42. But if I use by name with paren method, with parentheses, this is okay, and the compiler, the IDE is actually very smart to insert the parentheses for me. But if I copy this and I remove the parentheses, then this is also okay, but beware. The paren method here is actually called. So this is actually equivalent to by name with paren method like that. So I'm not calling by name with the actual function as if by name is a higher order function. All right. So the confusion that arises here in the situation is that people confuse the by name parameter with a higher order function, and they expect by name with a function to actually use the function itself inside. But in reality, it only calls the method, and by name actually uses that value, not the function itself. So be very careful about the distinction between by name parameters and function parameters. They are completely different. Now, by name with a lambda obviously doesn't work because, like I said, a by name argument of a value type is not the same as a function parameter. All right, so this is not okay. I'm just going to comment that out. If, on the other hand, you say by name of a lambda with 42, and then you call that lambda like this, then that's fine, because you basically supply a function here and you're also calling it, which turns this whole expression that I've highlighted here into a value. All right. By the same line of reasoning, by name with a partially applied function like paren method like this is not okay, because this guy is an expression which is a function value, and like I said, a function value is not a substitute for a by name parameter, so this is also not okay. All right, so let's now use the by function method. So if I use by function with an int like 45, obviously this is not fine because this is an int and by function expects lambda, so this is not okay. This should be pretty basic. Also, by function with a method, with a parameterless method is not okay. But this is very important because you would otherwise expect method to be converted to a function value, but method here is actually evaluated to its value 42. So the compiler does not allow you to write such a call. So this is very, very important. Parameterless methods like accessors without parentheses and proper methods with parentheses are different in the sense that they cannot be passed to higher order function. The compiler does not do eta expansion here. So be very, very careful. If, on the other hand, you call by function with paren method, just like that, then the compiler does eta expansion. All right, so this is the difference between accessor methods without parentheses and proper methods with parentheses, is that the compiler automatically does eta expansion for us. Okay, of course, by function with a lambda also works, like 46. This works fine because this is a function value, so this works as expected. And also by function with paren method underscore, this also works. But as in the previous example, this is a compiler warning saying anonymous function convertible to method value. That is, the underscore here is unnecessary because I'm basically telling the compiler explicitly, hey compiler, do eta expansion for me, but the compiler doesn't need to hear that from me because it can do eta expansion on its own by just calling a higher order function with a method. All right, so this also works, but warning, unnecessary. All right, so I hope this clears some of the confusion that I normally see with methods being parentheses-less versus having parentheses, and by name arguments versus function value arguments. All right. All right, so what have we learned? We started by getting our background straight about currying and curried function values and curried methods with multiple parameter lists, and then we discovered partial function applications, which are a way of telling the compiler by providing special underscores to provide eta expansions for us, that is, turning methods into function values. So this is called lifting or eta expansion. Then we saw that underscores are actually very powerful, that by providing a typed underscore, you can reduce function arity, that is, convert functions from many parameters to fewer parameters. All right, so this was quite a long lesson, but I hope it was worth it. I'm Daniel, and I cannot wait to see you in the next video.